Did everybody get an email from me? You should have gotten an email from me, I think, on Friday night. No. Yeah. It had the video from Friday. It had the video from Friday in it. Okay. Okay, here we go. In your notes, we will approach all problems from multiple perspectives. The best way to understand a problem or concept fully is to view it through multiple perspectives. Anybody ever here been a witness to an accident, a car accident? Okay. What do the police do when there's an accident, say like it's on Main Street or something? After they arrive at the scene, talk to both the drivers, right? Okay. They talk to anybody else? Most of the time they try to get multiple perspectives on that, because you can imagine if there was an accident on the road, this is one car here, hits another car here. Well, they have their own perspective, but if they can get witnesses from these different places, they can kind of piece together what really happened, because each one might have their own story, but when you put the whole thing together, then you start to see the clear picture. And that's what we do with all problems, not just math problems, but not just what I'm going to teach in calculus, but you should do that in life in general. All right, so what do I mean by that? First one, we're going to approach problems analytically. That means using algebra. So the numbers and the variables, and that is part of the analytical approach. The second way that we're going to approach problem is graphically. Okay. And that's usually some sort of coordinate plane or some kind of picture that represents what we're doing. Remember, it's the same thing, but viewed in a different lens, viewed through a different lens. And the third one is numerically. And this is where we maybe just plug in numbers. Okay. Remember, same problem, but just viewed from 3 different perspectives. Now, all of these things are planning on allowing us to describe something narratively. Okay? So, the goal here is that not only can you understand something fully, you have the ability to explain it to somebody else. Okay? That's key. That's huge. On the AP Calculus exam, there's really two main things. You have to be able to read technically, and you have to be able to write technically. So this class is a lot about reading and writing technical information. Okay? And so I'll be honest with you. You guys are talented. You have a lot of attributes that are good. Many of you will end up with jobs where you're in charge of other people. Okay? And what does a good boss need to be able to do? They need to be able to communicate to the people. They need to be able to explain things in a good way. In fact, one of the strongest attributes of a leader is their ability to take some stuff that's really complex and to explain it to people in a really simple way so they can understand it. That's what your challenge is as you go throughout all of the stuff that we do all year long. All right, I want to model this for you. So what I want to do is I want to graph the natural log function. Okay? So the natural log function, I do have to have this like in front.
Yeah.
If I turn around, then it doesn't work as well. So we're going to, I'm going to explain how this works. So let's understand and graph y equals ln x. By the way, can everybody do that right now? Do you know where all those points go and why they go where they go? It's okay if you say no right now, okay? But when we're done, then you should understand, and you understand why. It's not just this thing that goes like this. Well, I know it goes like this somehow, okay? But where it starts and where it stops, those things matter, okay? Everything, we have to understand why it looks like it does. Okay, so we're going to approach this analytically, graphically, and numerically and see how this works out so we can figure out how it goes. So our goal, let's graph y equals ln x. Where do you start? You're not allowed to use your calculator. One? One. Lost. Plug in numbers, okay? So oftentimes we've made a t-table, right? Okay, so we can make a t-table, and then this is my function, y equals ln of x, okay, where what's going inside the parentheses is what the input is, okay? And then we all remember the function box, right? Input and output, and that's how that works. So we're putting these numbers in, and we get them out. Okay, so 1, that was a good one. 1. What is the natural log of 1? Because this is what we're doing. We're doing the natural log of 1, and we're getting an answer. You sure he's right? What is the answer? Natural log of 1 is 0? Okay. Why? Because e to the power of 0 is 1. Where did the e come from? E is the base of the natural log. Okay? Let's do let's do some recalling. So over here, this is like background stuff that's kind of important. So you remember y equals log of x? Okay? Log of x. I always forget what that is. Somebody look it up. Go online right now. Look up, pull out your phone, Google, what is a logarithm? Megan's going at it.
Preference for a logarithm.
And you can just say define logarithm.
Quantity representing the power to which a fixed number, the base, must be raised to a product of a given number.
Okay, say that one more time.
A quantity representing the power to which a fixed number, the base, must be raised to produce a given number.
Okay, so this whole concept, have you heard? Well, logarithms are exponents. That's all they are. Well, they are the log, this right here, this answer is the exponent on the base. So what we really say, if we don't write the log, the base, then it's called the common log, and it's base 10. Okay? Your calculator is it has base 10 built right into it. It says log. Okay? So when I say things like, okay, let's do this over here. Let's do x and y equals the log, and I know it's the base, and I say 1 here, then what I'm really wondering is 10 to what power, okay, is equal to 1? That's what it's asking. And so what's the answer? 0. So my answer, the thing that goes in the t-table here, is the exponent. And so this is my answer. You plug in a 1, you get a 0. Okay? All right. 2. Because that's what we always do, right? We go like 1, 2, 3, 4, 5 on a t-table. Okay. So 10 to what power gives you 2? Give me a guess. Give me a guess. 0.2. Okay, now pull out your calculator and take 10 and raise it to the 0.2 power. I'll do that all year long. 10 to the 0.2 is how much? 1.584. Okay, so we're close there, right? What is 0.3? Oh, okay. So this is pretty close to around 0.3, right? Okay. And that's 10 to the 1/3 power. Okay? Take your calculator and do this. 10 and raise it to the 1/3 power. Roughly, it's close. Did you get an answer right around 2? 2.5? 2.15. Okay, so 2.15. So what we're seeing here is the answer to the log thing, the log function, is the exponent that we need to raise 10 to in order to get the number that we started with. Okay, what's a really easy number to put here now? 10. Okay, so 10. What's the answer here? 1. Okay, test it on your calculator. Take the log of 10. Okay, log of 10. Next one would be easy. Log of 100. Punch your calculator. What's the log of 100? 2. Okay, so this is the log function. This is the basic logarithm function. And what we notice here, when we're just doing little sketches, if I do 1, I get 0, right? But then I have to go out to 10 to go up 1. You see that? And then I have to go way out to 100 before I can plot a 2. Okay? So this part of it gives you this effect right here. Okay? It goes up, it grows, but it grows really slow. Really super slow. Okay? All right. We're going to take this concept now, because here's the deal. Calculus doesn't use log base 10 at all. We only use natural log. Okay? So from now on, E and the natural log will be your friend. Okay. All right, Christina said something about the natural log having a base of E. Okay, so that means this. Y is equal to the natural log of x, which is really the same exact thing as the log base E of x. Those two are the same thing. It's the log, but it's a base E. Okay, so let's apply what we just did over here and try to fill in a little table here. Someone ask the next logical question. What is it? What's E? See, that's how this works, okay? That's how this works. We're trying to go your natural way of thinking. If we're supposed to do this, don't we need to know what E is? Okay, look up E. Okay, E is 2.718281828, okay, and so on, but it does not repeat, okay? E is, what do they call it, a non-repeating, non-terminating? It's an irrational number, okay? It has special properties, okay? It's a really, really cool number. It was named by Leonard Euler, who is on the wall, third guy from the left. A lot of times people pronounce his name as Euler, but it's actually Euler. And he named it after himself. Okay, that's what you get to do when you really figure something out. So E is a constant, just like pi is a constant. Okay, it's just this number, but it's a special number. Okay. So back to here. Now that we know that, this meant here that e to the 0 was equal to 1. That's the connection here. And the answer, just so we make sure that we see it, the answer is here. Okay. 2. What would it mean to take the natural log of 2 and get an answer? What would it mean? E to the something is equal to 2. Correct? That's what this is saying. Okay. So what was E? E is about 2.7. So what kind of a number would we need to raise E to in order to get an answer of 2? Is it bigger than 1? No. You can tell that why. Because e to the first would be e, 2.7. Okay, so it's got to be a little bit less than that. Okay, so on your calculator, give me a decent estimate without using the natural log function. Take e to some power and get me 2. 0.7? Okay. And again, we're just, this part right here, we're kind of doing the numerical part. We're plugging in numbers and we're seeing what's going on here. Okay, so I can do a natural log of 3. Okay, any guesses? Is it over 1? Is it over 2? No, 2. E squared is probably like 8 something. I guess it's full now. 1.1, okay? So we're talking 1.1 here as the answer, because e to the 1.1 is about 3. Okay? These are points that we're plotting because we're making the table based upon that we understand where it came from. Okay, so follow what we did over here. What's a really easy one to do over here? E. What is the natural log of e? 1. Okay. The natural log of e is 1 because e, the base, raised to the 1, is equal to that e. Okay. What about e squared? What is e squared? What is the natural log of e squared? 2. That's what I'm hearing. Agree? Okay, I'll write down 2. Why is it 2? It's the exponent on e that gets you what you started with. Okay? In other words, watch this. The natural log of e squared is equal to 2. Because e, the base, that we don't write, e squared is equal to e squared. Okay? Natural log of e cubed, 3. Anybody notice a pattern? You learned a rule last year in in logarithms. What rule am I referring to? I'll write it in a rule form. So in general, natural log of e to the n is equal to n. Wait, where'd the natural log of e go? What do you mean cancel out? Natural log of e is 1. So, you remember that thing? Oh, you just bring it down, right? You just bring that exponent down, okay? This is equal to n times the natural log of e, which the natural log of e is 1, so that's why the natural log of e to the n is equal to n. Make sense? Okay. All right. Now it's time to plot the points and see what we get. So, here we go. By the way, you know you're going to be tested on this, right? Where I'm going to give you blank sheets and I'm going to say, draw me this function accurately with dots and all that. Okay, without a calculator. Okay, so I'm going to plot a couple of points here. So, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not any points here. We're going to go up here. 1, 2, 3. Well, what do I got? Natural log of 1 is 0. That's right here. The natural log of 2 was about 0.7. It's like right around there. Natural log of 3 is a little over 1. Okay. Natural log of e. Where's e on this bugger? E's about right there. Agree? It's 2.7. There's 1, 2, 3. That's where e is. That's where I'm smack dab on 1. See that? Okay. Where's e squared? What's e squared? So 7.3. Okay. It's this number times itself. So 5, 6, 7, here's 7, and the natural log of e squared, you said it was 7.3 something? Yeah. So this is where e squared is, and this is going to be where the 2 goes. See that? So the growth of this thing, you can see, is super, super slow. It goes like this. It keeps going up, okay, but it takes a long time to get there. Okay. Yeah, great question. So that's excellent. That's where we're going. That's where we need to go next. Who said that? Libby. See? This class only works by participation. Okay, what's with the negatives? Like, is this the whole graph of the natural log of x? Okay, all right. So I'm going to continue this. So here's x, here's the natural log of x. What happens if I do -1? What is the natural log of -1? 1 over e. We good with that? Bitsy's shaking her head. Well, where would this go? What? Can't take the log of a negative number? Why would that be? Okay, let's just test. Try to find natural log of a negative number. It's a non-real answer. Okay? Everybody get undefined error, something like that? No? Okay. Okay. So 1 over e. So what we're getting here is this is undefined, which means there's no point. There's no plot. There's no point that we can plot. Okay, but I want to know why. Why can't you take the natural log of -1? Yes? Okay, so let's test it. What does this mean when we're taking the natural log of -1? It's e to some power is equal to -1. Okay. Can you take a positive number, raise it to a power, and get a negative answer? No, because even if we put in a negative number here, what's e to the -2? It's 1 over e squared, right? That's how we work with negative exponents. The answer is not negative. We take the reciprocal of it. It's 1 over e squared, so it's a very small number. Okay? So what that means is over here on the left side, okay, -1, -2, none of those numbers produce anything when we plug it into the function. We plug those negative numbers in, and we get nothing that comes out. Okay? They are not part of the domain of the natural log of x. Okay? So no negative numbers here. Okay, I guess what's 0 then? What's the natural log of 0? Well, when in doubt, we think about it numerically. We say e to what power can give me 0? Okay? No number, no real number. Okay? Because, once again, we have e to some power, making it 0. I know this for a fact, that the only way you can get 0 is if you have a fraction and the numerator is 0. That's the only way you can get it. This is e. This is e over 1. It's the same thing. That's never going to be equal to 0, ever. So 0 is not included in the domain. Okay? You can't plug those in. But what I'm noticing is there's a little space in between here. So what about 1/2? Is it legit for me to take the natural log of, say, 1/2? And if so, what does it mean? E to the something equals 1/2. Is it legal to find an answer? Can we find something that makes that work? This means e to some power is equal to 1/2. Go find me something that's close without using the natural log key. Without using the natural log key, find me the answer. E to some power is equal to about 1/2. Just get in the ballpark. What do you get? Negative 0.6. Anybody else get something like that? So look at your graph. So as soon as we go between halfway between 0 and 1, we're right at 1/2. The answer now is this negative 0.6. See that? Well, what if we go even closer to 0? Let's do 1/10. What is the answer to the natural log of 1/10? Negative what? What do you get? Negative 2.3? Okay. So that's even further down here. Okay, but we're getting closer and closer to the y-axis. I need to justify this or verify this. This means e to the negative 2.3 is equal to 1/10. That's what that means. E raised to the negative 2.3 is going to give me around 0.1. Okay? And notice this is this is the same as 1 over e to the 2.3. Means that e to the 2.3 has got to be around 10. See, we're justifying it numerically, seeing how this all works out. Well, what happens here? As you get closer and closer to the y-axis, with our x values, the values for the answer of the natural log become more and more negative. And what we have here is an asymptote. We never can plug in x equals 0, but we can get pretty doggone close to it. Okay? And the closer you get here, so what this means is take your calculator and do something crazy like natural log of 0.00005. Go ahead and do that on your calculator. There should be some crazy negative number. Negative what? Negative 16. That's pretty crazy. It's not so crazy. Okay. So the whole graph, this is what it looks like because we developed from scratch. We analyzed it analytically and numerically and graphically, and this is what we end up with. Okay? You need to be able to understand every single one of the functions at this deep level. Yes?
So if you guys are still like graph this, would you prefer to start at like 1 or 2 and go all the way down?
You have to give me, I would say give me like 2 points right here, Give me the natural log of 1, that's biggie, and then 2 over here would be good. Okay? So you have some sense of what it looks like. Okay. I'm intending for us to do trig functions tomorrow. Okay? So without a calculator.